The sampling distribution for a difference in sample means x1 bar minus x2 bar is typically used when you want to do inference where you're comparing two population means, mu1 and mu2. The way you do it is you draw two independent simple random samples, one from one population, the sample size would be n1, and the other sample size would be n2, drawn from another population. Now, if the populations are both normal, we'll assume that with means mu1 and mu2 and respective standard deviations sigma 1 and sigma 2. If the samples are independent, then the sample means x1 bar and x2 bar will be independent also. And we can also make other claims about the center, the spread, and the shape of the sampling distributions for x1 bar and x2 bar. If the populations are normal, then x1 bar and x2 bar will both be normally distributed. Since they are unbiased statistics, their means will be equal to mu1 and mu2 respectively, and their standard deviations will be equal to sigma 1 divided by the square root of n1 and sigma 2 divided by the square root of n2 respectively. So this is what we get out of all that, is that x1 bar is normally distributed with a mean of mu1 and a standard deviation of sigma 1 over the square root of n1, and x bar 2 is normally distributed with a mean of mu2 and a standard deviation of sigma 2 over the square root of n2. Now what we're interested in is using that information to say how the difference between x1 bar and x2 bar will be distributed. Now when you're talking about the distribution of any random variable, you always want to talk about the center, the spread, and the shape. So let's look at that next. The center of the distribution, the mean of x1 bar minus x2 bar, is equal to the difference in the means of x1 bar and x2 bar. It's just the basic rule for means. When you want to take the mean of a difference in two random variables, you just take the difference in their respective means. Now, x1 bar has a mean equal to its population mean mu1, and x2 bar has a mean equal to the population mean mu2. So the mean of the difference between x1 bar and x2 bar is equal to mu1 minus mu2. That means that x1 bar minus x2 bar is an unbiased estimator of this difference in population means. And in terms of the spread, we use our rule for variances. The variance of x1 bar minus x2 bar is the sum of the variances of x1 bar and x2 bar. Remember, variances always add. And each of these variances is equal to the population standard deviation squared divided by the respective sample size. And then to get the standard deviation of x1 bar minus x2 bar, we just take the square root of that expression right there. The shape is normal. x1 bar and x2 bar are independent normal random variables, so their difference is also normally distributed. So what we get in sum out of all this is that x1 bar minus x2 bar is normally distributed with mean equal to mu1 minus mu2 and a standard deviation equal to the square root of sigma squared 1 over n1 plus sigma squared 2 over n2. Now we could apply that to different kinds of examples, although mostly we want to apply this to inference involving two population means. You could answer some questions just about this particular sampling distribution. For instance, suppose we have two populations, 1 and 2. The mean of population 1 is 15 and the mean of population 2 is 12. The standard deviations respectively are 4 and 3. And we draw samples of size 50 and 60, and those samples are random and independent. The mean of x1 bar minus x2 bar is just the difference in the population means, 15 minus 12, or 3. The standard deviation is a little bit more complicated. We have to use this formula and plug in the standard deviations and the sample sizes from the two groups. And when we simplify it down, that simplifies down to the square root of 0.47, which is about 0.6856. Then we could answer questions. Suppose we want to know the probability that the difference in these sample means is greater than 4, given that they come from those populations that we gave parameters for above. This is just a standard normal calculation because x1 bar minus x2 bar is normally distributed. So we subtract the mean, divide by the standard deviation on both sides of that inequality. This big mess right here becomes a z. 4 minus 3 over the square root of 0.47 is 1 over the square root of 0.47. And when you plug that into your calculator using normal CDF, you get that probability is about 0.0723. If you want to find the probability that the difference in the sample means is between, say, 2.5 and 3.5, you can do a standard enrollment calculation there. Standardize both ends. The middle will become a z, and when you standardize both ends and then put those into your calculator as the boundaries for normal CDF, left boundary, right boundary, you get about 0.5342. So you can do standard enrollment calculations with the sampling distribution. But again, that's not primarily why we use it. We use it so that we can do inference where we're comparing two population means, either for a confidence interval for the difference in two population means, or a test of significance involving a difference in two population means. And that's what we'll turn to next.